of tutorials. I know everybody's starting to get tired, but thanks for being here. So I'll talk very briefly about fairness in visual recognition. I want to first of all give a big shout out to all of my, or I guess this is only actually even a subset of the students who've contributed to this, to some of the work that I'll talk about today. So first of all, when it comes to fairness in visual recognition, right, what do we mean by that, and what are kind of some of the reasons why we're working on this problem? So over the past about 5 years or so, as computer vision started being deployed kind of all over the place, there started to be, it kind of started to work, but also there's kind of an increasing number of these sort of drastic failures and problematic failures of computer vision systems. And so this is things like computer vision model that learns to quote unquote increase attractiveness by actually manipulating skin color. So this was a photo app filter that was released that claimed to manipulate, that claimed to sort of increase the attractiveness of a photograph. Now, why somebody would do that is a whole other question, but putting aside that issue, in practice, what this model ended up learning is to sort of change your skin tone in an effort to make it more attractive. And that is obviously a very, very problematic behavior by the model. And then there's a lot more examples, right? So machines taught by photos learn a sex appeal of women. Facial recognition is accurate if you're a white guy. So this is seminal work I'll talk very briefly about later in the talk by Joy Bellamini and Timmy Gebru that sort of showed that face recognition systems have very, very different levels of accuracy. So they work really, really well on faces of light-skinned men and work very, very poorly on faces of dark-skinned women. And this has a number of course, downstream applications and downstream sort of implications, including when facial recognition is used in high impact settings like criminal justice. And then, of course, a recent controversy on Twitter with a cropping algorithm that prefers lighter, slimmer, and younger faces. So all of these issues, right? They're very complex and they're really socio-technical. They go beyond just the algorithmic questions. And there's lots of excellent literature, like for example, the work by a colleague at Princeton, Professor Ruha Benjamin, called Race After Technology, that really grapples with the social implications of these issues, both the root causes and the downstream impact. So when we work on fairness, we simplify all of these socio-technical issues into a much simpler cycle. So we say, okay, there's some kind of human history bias and prejudice that's made its way into large-scale data that then becomes part of AI models, or it's learned by AI models, becomes part of AI decision-making, and then that becomes part of our history. And so the question that we ask from a technical perspective is, can we adjust the AI design to try to mitigate some of these effects, to try to mitigate some of this bias propagation? And so we can kind of look at different pieces of the cycle and think about what would it take to design interventions there. So for example, if we look at the large scale data piece, right? So the key there is that large scale does not necessarily mean fair representation. So there's sort of this tempting narrative of, well, I'm just going to take all of the data that's available on the web and I'm going to use that to train my models, and then I don't have to worry about fairness. But of course, there is all kinds of issues that can come up. The perhaps simplest or most salient is the question of demographic diversity. And so this is again, the work by Joy Bellamini and Timmy Gebru that I mentioned. So one of the things that they pointed out in their paper looking at accuracy of face recognition models is that modern face recognition data sets contain primarily people of lighter skin. And by primarily, I mean 80 to 90% of these data sets were people with lighter skin. And so this does not necessarily explain fully the discrepancies in error rates of the classifiers trained on these data sets, but at least helps give you some sense of, well, what might be going on there. Well, there's a drastic underrepresentation of people of darker skin in these data sets. Another kind of tempting narrative that you might say is, well, okay, maybe none of this fairness stuff actually applies to me if I don't work on faces or if I don't work on people recognition at all. And that's not true for, in particular, for the reason that actually Biraj and Judy already talked about with geographic diversity. So these data sets contain photos coming from particular geographic regions and have an overrepresentation of photos coming, for example, from the US, and very few photos coming from, for example, the entire continent of Africa. And again, as Gresh pointed out and Judy earlier today, this leads to errors in even, for example, object recognition models that fail to recognize bar soap because they've been trained on US-centric images and they've learned to recognize only US brands of liquid soap as a representation of what soap looks like. And so these kinds of fairness issues can come up, right, even in something as seemingly innocuous as object recognition. And the part of the cause of some of this is of course, the lack of diversity or the stereotype representations that are returned by image search engines. And there's a lot of work pointing out how when you type a particular term into an image search engine, the results may be biased along a number of different dimensions. So for example, this is work from, it was published in 2015 in Kai that analyzes the image search results when you query for different occupations of people. So if you query for something like CEO, the results that you get tend to be, first of all, more male focused than even sort of the number of the percent of CEOs who are actually men. In reality, the search results tend to be even more skewed towards male. And in addition, give again this kind of Western stereotype portrayal of what a CEO looks like, how a CEO dresses, and so forth. And so, of course, when we use internet as the internet as a source of our visual data, we inherit a lot of these biases. So in addition to these questions of representation within data sets, there's also this very rich literature on data collection practices. And I'm not gonna dive into this, but I would encourage all of you who are kind of interested in this space to engage with some of this literature. This has been published. If you notice, all of these papers I'm citing are basically 2020, 2021, 2022. This is very much a recent and growing set of works looking at things like privacy and consent and ethics of data collection, who is being included, who is being compensated for their work of taking photographs, what happens if sort of somebody takes a photo of you and posts it on the web, and then does that implicitly give consent for this photo to be included in a computer vision data set, and how do we sort of grapple with all of these issues? And in particular, how do we grapple with these issues in the international context where the legal guidance may be very different across different countries? But what I want to highlight is a couple of our works thinking about this question of trying to understand the biases of within large scale data sets. And the first one that I want to sort of again briefly highlight is called Revise. So this is Revealing Visual Biases tool. And so our goal here was to set out to develop a tool that takes as an input a visual data set and then reveals potential social biases in the data set. So the issue, right, is that these data sets are very large scale. They were collected from the web or wherever they were collected. And it's very hard to understand sort of what is actually in them, or do they have particular biases that we may want to be aware of when actually training models. And so the contribution, this was originally published in ECCV of 2020 and was recently accepted to HACCP this year. So the contributions here were trying to aid dataset creators and users by revealing biases in large-scale visual data, kind of in a semi-automatic way, where the tool sort of says, okay, here's a set of things that I found, and then leaves it up to the user to interpret or analyze or sort of intervene upon them. So in order to do this, we're leveraging the available annotations. So if there's any annotations available for the data set, we will use those, as well as pre-trained models if there's no available annotations, as well as census data. If we have, for example, GPS tags, and grab census data and use that to compute some statistics of the data set. And the goal is to identify bias in the representation of objects, of people of different demographics, and of geographic regions. And then the tool also suggests some quick actionable insights to the user in terms of what they might want to do to diversify the data. So let me show you one particular example finding, right, and then we'll refer you to the paper to learn more. So here's an example finding. So the images here are the COCO data set. there's two annotations that were used. So one is gender annotations, and I will see here, so these are binarized, socially perceived, inferred gender expression annotations. So this is a significant simplification of the concept of gender, which is of course non-binary, but here we are just looking at sort of binary labels, male or female. These are annotated on photographs by people basically mechanical Turk workers who looked at these photographs and sort of try to infer what the gender of the person might be in the photographs. And further, these are actually derived from image captions in an automatic way. So there's a lot of issues and subtleties and nuances with these labels. This is what we have available, and this helps at least give us some sense of statistics in the data set. The second type of annotations are predicted scenes automatically using the places model. So this was actually developed by Bolle and his co-authors. And so this is, we don't have scene labels on these images, but we can run this pre-trained model to try to get those. So now here on the y-axis, I'm showing the output of this scene model, so the different types of scenes that were discovered. In the x-axis, I'm showing the fraction of images with this scene and images with people who appear to be male versus female. And so you can see some patterns in here, right? So things like outdoor sports fields and parks appear to have people who are predominantly male, and then shopping and dining scenes have people who are predominantly female. And so you may want to ask, right? So what does this mean, and is this okay, and is this reflective of the world at large? And as a dataset creator, is this a kind of pattern that I am okay with, or that I want it to be represented in the data set, or do I want to sort of intervene in some way and rebalance the data set? And so there is a lot of work right now in computer vision fairness that says, okay, these data sets are going to be biased in particular ways. And for example, there's sort of gender bias in these data sets. So now I want to try to intervene upon this. And in particular, I want to train sort of models from these representations that are invariant to, for example, the concept of gender. So I want to train a model that is completely gender blind, that completely removes, gender cues from the data set, so I don't have to worry about gender bias in the models. And so I will show you sort of one result. So this is something that is part of the process we just submitted to archive. So I think it's not on archive yet, but it will be today or tomorrow. So we are looking at gender artifacts in visual data sets. And the question we want to ask is to understand actually the extent to which gender artifacts are present in the data set. So in the previous example, right, with revise, I showed you, okay, maybe people of different genders are more correlated with different scene types, but like, how prevalent are gender artifacts actually in a data set like Coco? And so what's happening here? So this is one result from this larger paper. So I'm showing on the y-axis the ROC AUC, so basically the accuracy of a gender artifacts model. So this is a model that's trying to classify the image as whether it contains a person labeled female or male. Again, the images are the Coco data set, and the gender labels are the same as before. On the x-axis, I'm showing the different resolutions of the image. So as we sort of decrease the resolution of the image, you can see how it becomes sort of more and more pixelated and less visible, less and less understandable. So the different lines, so the blue line at the top shows color images at different resolutions, and sort of the accuracy, right, of this gender artifact model on these images at different resolutions. The gray line is the same thing in grayscale. So what's the first thing you want to notice? So the pink line at the bottom is actually random chance at 50%. So for color images, even as low as 7:7 resolution, you're able to reliably predict whether the image contains a person who appears to be male or contains a person who appears to be female, right? Even at 7:7 resolution. And even more so, we've got this purple line, which is actually a model trained on just 3 features. So this logistic regression model trained on 3 features, which is R, G, and B. So the average image color of the image. And we're able to do, again, significantly above random chance in predicting whether this person is likely to be male or female. So what does this tell us? So this tells us that these gender artifacts, these gender visual cues that are correlated with gender are very, very pervasive in data sets like COGO. And actually, I mean, we've ran analysis on open images, for example, as well. So this suggests that if we're trying to build models that are mitigating bias in these data sets that are sort of invariant to, for example, gender cues, we have to be very, very careful because these cues are very pervasive and they're sort of everywhere. So any kind of simple intervention will not work to obscure gender cues. So we have to sort of learn to live with them. And so now we can talk about, right, so how do we, given that there is always some kind of bias in the data set, right? So we need, on the data set side, we need targeted interventions, right, to increase representation, to examine and understand the data, to constructively engage with the raised ethical issues. But ultimately, this kind of bias is always present in the data set. So what can we do on the model side? So what can we do to actually try to mitigate this bias? And there's a lot of things that we can do and a lot of challenges in building fair models, right? So there's work on trying to understand bias propagation. So I've talked about these gender cues, right? But one question that kind of naturally comes up is, are they actually going to be harmful in downstream models? Like, first, are they going to be learned by downstream models? And second of all, are they going to be harmful, right? And so there's a line of work trying to understand kind of under what conditions this happens. There's a line of work looking at interpretability and interpreting the models and trying to figure out what it is that they've actually learned, and are they relying on any of these, for example, gender cues or racial cues or whatever may be in the data set. There's a line of work on looking at being right for the right reason. So making sure that when you're making predictions, you are relying on sort of the parts of the image that are actually relevant to the prediction instead of on spurious correlations. There's a very rich literature on quantifying fairness. So how do we actually measure what fairness is? And how do we measure whether our models are biased, unbiased, under different circumstances? Of course, very rich literature on actually mitigating model bias once we quantify the metrics, right? So how do we actually implement this in the model? And finally, engaging with the broader social context. And I'll say actually right now, so the Fairness, Accountability, and Transparency Conference FACT is actually going on in Korea right now, unfortunately, simultaneously with CBPR, but that has a very rich line of work on sort of the connections, sort of the social technical connections between the some of the algorithmic work as well as the social impacts. So rather than diving into this, so I'll actually stop here because I will pass it off to Ruth, who's going to talk about interpretability, both in the context of fairness and much more broadly. So Ruth is an expert in interpretability, and all of the work that we've done has actually been in collaboration with her. So we've been incredibly lucky to get to work with her on this. If you're curious to learn more about the fairness side and some of the fairness interventions, so I'll actually give a shout out to gave a tutorial yesterday together with Sam and Korea Joe on algorithmic fairness, why it's hard and why it's interesting. So this was basically 3.5 hours of content around algorithmic fairness. We'll make the recordings available and the slides available, and so I will refer you to that. And now I will pass it off to, I guess I'm happy to take a couple of questions, and then we'll pass it off to Ruth, who will talk about some of the interpretability work. Yeah, if you have questions, feel free to come up to the mic.
Talk about device and its implementation. I have a question.
Yep.
Do people come up with a new data set, which is not so well allocated in terms of social context and stuff like that? And we want to understand how bias at the gender, race, or geography mitigate. Should we use some sort of like along the device or use a deep learning model to use that as bias of that? So what's your take on a new data set and trying to come up with an analysis of what's the right one that is not so well?
Yeah, that's a great question. So the question was, so in case folks didn't hear it, the question was, so revise, I presented a result on COCO, but what happens when you have a new data set, in particular a new data set that has fewer annotations? So we tried to revise on a large set of different data sets. So essentially, revise by itself, right? So it'll try to get as much information out of a data set as possible. So if possible, it will use existing annotations. If not possible, it will run a bunch of pre-trained models. Yes, you are correct that these models may be biased. That is true. So are human annotators. So I think the bias in the annotations, that is always something you have to sort of be aware of and take into account. There's also a lot of work on sort of unsupervised bias discovery. In particular, Judy has actually done some work on this. So she has some work on kind of unsupervised analysis of data sets and bias discovery. So there's definitely some work on that. But ultimately, right, I think there's always sort of this trade-off between like how much can you do automatically versus how much do you get annotations, and there's also the question of like who's doing the annotations and how does that factor into the analysis again. Sort of, yeah. Yeah.
It requires, always requires human knowledge, right? Instead of looking at the data, really don't want
yeah, so it's a great question. So the question is, how do you discriminate whether it's a bias or a useful feature? So we try to give a lot of sort of answers to this in the tutorial yesterday. The short answer is a lot of the time, you can think about bias from a harms framework, from the framework of sort of, are these predictions harmful to somebody or harmful in some way to some, and there's sort of definitions of what are the different types of harms and so on. So I think that's kind of how I think about bias and fairness questions versus sort of, you know, questions of spurious correlations more generally, or just questions of like, yeah, the model learned what it learned and did the best it could, and you know, even if it doesn't learn the right feature, okay, so but it still does well on the test. So that's sort of the distinction we make. Mm-hmm.
Okay, thank you for that great talk. I'm Shen from NYU, and I have a question regarding like you just show us like a lot of bias data set. And my question is that does bias data set always lead to a bias model, or in this case, it will lead to, because we know that, for example, we see, for example, the data set contains a lot of men playing like outdoor sports. Is that always true that the model will like, you know, this data set will like also learn on men instead of learning how to classify or do jobs sometimes?
Yeah, so that's an excellent question. So does a biased data set always lead to a biased model? So the answer is no. The answer is definitely no, right? So a model will pick up on whatever cues sort of from the data set and not necessarily pick up on bias. So actually, so let me go back here for a second. So this understanding bias propagation, I don't know if you can see my mouse, but the understanding bias propagation, so a lot of that literature is actually asking this exact question. And so the last work that I'm citing here by Dora Zhao and Angelina Wang and myself called Understanding Racial Bias in Image Captioning, I think published at ICCD last year. So we actually looked at kind of under what conditions does bias from image captions propagate into learned models. And it turns out that for some of the older image captioning models, they don't capture any kind of racial or gender bias because they're just not super descriptive. They say generic things and are pretty robust to any kind of biases in the data, whereas the newer models, right, the ones that are actually producing much more detailed descriptions and have much more capacity, they actually tend to be a little bit more biased.
Yeah, and like it's not true that is there any general something that more like there are like a general case
yeah, so I think the question is, are there general principles under which the model will capture biases? So I think the general principles are the model will capture the most visually discriminative cues, right? So that's the high level general principle, right? And as we've shown in the result with gender rates, so something like gender even in a data set like COCO rates, so those sort of features that are correlated with gender appear to be quite discriminative, quite robust, which suggests that it's likely that the model will be capturing those, and then by virtue of capturing those, that will be capturing some kind of correlations with gender. So yeah, that's the short answer. Yep, absolutely. Okay, last question, and then we'll move on to some.
Question about the bias.
Mhm.
Obviously,